The Nash equilibrium is one of the most well-known and most studied solution concepts in game theory. There's quite a lot to learn about them. To start, we will look at a relatively simple class of games known as two-player zero-sum games. As the name suggests, these games involve only two players. Zero-sum refers to the fact that for every strategy profile, if we add up the payoff of both players, the result has to be zero. In other words, whatever one player wins, the other player loses. Let's say that the first player has M1 many pure strategies. In other words, we can imagine that her strategy set S1 consists of all integers between 1 and M1. And let us say that the second player has M2 many pure strategies. So her strategy set is S2, consisting of all integers between 1 and M2. For zero-sum games, we have that for any pure strategy profile, so one pure strategy S1 for player 1, and then one pure strategy S2 for player 2, the payoff to player 1, so P1 of S1 and S2, is equal to minus the payoff to player 2, so minus P2 of S1 and S2. We can specify the payoff to player 1 for each pure strategy profile in form of a matrix, and this will turn out to be very convenient. The rows of the matrix correspond to the pure strategies of the first player, and the columns will correspond to the pure strategies of the second player. Therefore, the matrix, let's call it A, would look like this. The payoff to player 2 would simply be minus the payoff to player 1. So we can express it as a matrix B, which is just minus A. Say player 1 plays the mixed strategy X, and player 2 plays mixed strategy Y. Remember that X and Y are vectors that specify for each pure strategy of the respective player with what probability that pure strategy is played. Then, what is the payoff to player 1? So player 1 plays X, player 2 plays Y. We have some payoff matrix A that expresses the payoffs to player 1 in each possible outcome of the game. So what is the payoff to player 1 in this setup? Can you see it? So it's simply X transposed times A times Y. We need to transpose X here so that the multiplications make sense, because we assume that vectors are column vectors at all times, but we need a row vector in this case. Of course, then the payoff to player 2 must be X transposed times B times Y, which just equals minus X transposed times A times Y. Let's illustrate this using an example, and I hope that will help you to understand what's going on here. Say both players have 4 strategies, and the payoff matrix A for player 1 is the following. Now, what does it mean for player 2? If player 1 chooses the mixed strategy 0, 1/2, 1/2, 0. What is the expected payoff for player 2 if she chooses the first, second, third, or fourth column? Right? Player 2 chooses a column, player 1 chooses a row of the matrix. Okay, so we can easily figure this out now by just multiplying this mixed strategy with the matrix. So we have 0, 1/2, 1/2, 0 times the matrix. In this case, we need to use the payoff matrix for player 2, which is just minus the payoff matrix for player 1. And if we calculate this, we get the vector 0, minus 7 over 2, 0, and minus 6. This is because, for example, the first 0 comes from 0 times minus 2 is 0, plus 1/2 times minus 3, plus 1/2 times 3 is 0 as well, and then 0 times 9 is 0. So if we add all of those up, it's just 0. But the minus 7 over 2, for example, comes from 0 times 23, it's just 0, plus 1/2 times minus 5 is minus 5 over 2, plus 1/2 times minus 2 is minus 1. So we have minus 7 over 2 now, and then plus 0 times minus 12, that's just 0. So the sum is minus 7, 2, and so on. So what does this now mean? It means that choosing the first column gives an expected payoff of 0 to the second player. The second column gives an expected payoff of minus 7 over 2. The third one gives an expected payoff of 0. And the fourth column, if the player chooses the fourth column, she gets an expected payoff of minus 6. So clearly, what player 2 would want to do is to either choose column 1 or column 3. The other two columns, column 2 and column 4, are much worse because the payoff there is actually negative, whereas at least in the first column or for the third column, the player gets a payoff of 0. So a best response to this strategy of player 1 would be to play either the first column or the third column, or any mix of those two strategies. But the strategy that corresponds to the second column or the fourth column should be played with probability 0 as a best response. Now, let's switch around the two players and let's think about the players in the other way. So what does it mean for player 1 if player 2 chooses some mixed strategy? For example, let's say player 2 chooses the mixed strategy 1/2, 0, 1/2, 0. What does this mean for player 1? Well, we can simply calculate this in a similar way as we did previously. We just take the payoff matrix of player 1, so this matrix A, and then we multiply it with the mixed strategy of player 2. So this vector 1/2, 0, 1/2, 0. And what we get is a vector, and this vector is minus 3, 0, 0, minus 4. And the entries of this vector tell us what the expected payoff is that player 1 will receive for each of her 4 strategies. So if she picks the first row, her expected payoff is now minus 3. The second and third row both give her an expected payoff of 0, and the last row would give her an expected payoff of minus 4. And clearly we can see that the player would want to avoid the first or the last row and just play some mixed strategy on the middle 2 rows. And now if we look at these two example strategies for player 1 and player 2 together, so we had for player 1 as an example, if player 1 chooses 0, 1/2, 1/2, 0, we can see this is actually just a mix of the two middle rows, right? Playing the second row with probability 1/2 and the third row with probability 1/2. So we see this is a best response to this example strategy of player 2, 1/2, 0, 1/2, 0. And now if we check, it's also the other way around. So 1/2, 0, 1/2, 0 puts 0 probability on the second and the fourth column of the matrix. And that's exactly what we would want to do if the first player plays 0, 1/2, 1/2, 0. So these two mixed strategies, 0, 1/2, 1/2, 0 for the first player and 1/2, 0, 1/2, 0 for the second player, are best responses to one another. And therefore, if we take both of those mixed strategies together, they form a mixed strategy profile that is a mixed Nash equilibrium. And we can simply investigate what the payoff is that player 1 gets from player 2 in this two-player zero-sum game by writing the mixed strategy of player 1, multiplying it with the payoff matrix for player 1, this matrix A, and then multiplying this with the mixed strategy of player 2. And if you do the calculation, it's just 0. So the payoff to both players in this case is actually just 0. Now, this concludes my introduction of two-player zero-sum games and the associated notation that I'm going to use. And in the following videos, we want to investigate whether Nash equilibria exists in those games and what type of properties Nash equilibria have.